All right, welcome everyone. My name is Sharon White, and I'm the marketing manager for BLT. Welcome to today's webinar, What is AXI? Before we get started, I just wanted to take a few minutes to introduce our speaker, BLT, and to go over some housekeeping. To get started, if you have questions, please put them in the chat panel, and we will get to them during the Q&A session at the end. Today's webinar is being recorded, and we will send that recording out once it's ready. There are no books or slides provided with today's talk. Now let me introduce you BLT and our speaker. BLT has been in the engineering design services business for over 30 years. We were started by one of the original Xilinx FAEs, and our headquarters are in Maryland, where we are today, and we also have an office in Melbourne, Florida. We design chips, boards, software, and complete systems for commercial, military, and intelligence clients, and our designs are in space, undersea, and everywhere in between. And we've been teaching AMD Xilinx training for 20 years. We're an AMD Premier Partner and Authorized training provider. Our training is by engineers, for engineers, and we bring our decades of real-world design experience to the classroom. And if you're interested in other training and events from BLT, be sure to follow us on LinkedIn, Facebook, Instagram, or the social formerly known as Twitter. We post all the latest updates on our social pages, and we also provide emails with what's going on. So today's webinar is being led by Ellie Rosen. Ellie is an engineering manager at BLT, primarily focused on adaptive SoC, RF SOCs, and MP-SOC designs for both commercial and defense applications, and he's one of our resident AXI and embedded experts. Ellie has spent many years managing AMD Xilinx-based FPGA projects, and before coming into this role, he spent countless hours designing, integrating, and debugging radar systems, underwater sensors, and cryptographic ASICs. He's also a general tech enthusiast that enjoys playing with SDRs and home automation on the weekends. And as you can tell by his t-shirt, he loves BLT sandwiches. So welcome, Ellie. Some other folks on our team, Lisa Weaver, she is our Senior Strategic Accounts Manager. If you have questions about what we do, our training, our classes, our design services, Lisa is your go-to contact. So I will put her information into the chat panel for you. So, all right, Ellie, I'm gonna pass it over to you.
Thank you for that, Sharon. I appreciate it. So to go over what we're going to talk about today, the real question here is, what is AXI? What is it used for? What describes AXI? The mechanisms that you can incorporate AXI into your design, and really how it plays a role into the day-to-day types of things that you might find in an embedded system. So we're going to cover what is AXI, the definition of it, the different flavors of AXI, the cores and related cores that you can find inside of Vivado. And then towards the end of this webinar, I'm going to open up Vivado and give a little demonstration of a memory mapped example, as well as a AXI streaming example that you can easily bring into your design so that you can get started with AXI. Finally, we'll wrap up with a Q&A. I welcome questions throughout this webinar. I will be monitoring the chat as we're going along. So if there is a question asked and I'm able to respond to it as we're going, I'm more than happy to do that. So to begin here, the AXI specification falls under the AMBA spec, and AMBA stands for the Advanced Microcontroller Bus Architecture. And within that family, this is a series of specifications from ARM. ARM is a IP company that creates processors that use the ARM instruction set. And within that family, there are a few different protocols here. I'll just cover just to name them, but we're going to focus on AXI today. The first one here, APB, is the Advanced Peripheral Bus. This is typically used for peripherals that you'll find inside of a processing system. This could be a UART, it could be I2C, CAN bus. These are interfaces that will go outside of the chip, but have a common APB interface to communicate with that peripheral. Next, we have AHB, which is the Advanced Host Bus. And this is a common protocol used by the processing cores to communicate with other processing cores, as well as various interconnects that then will communicate through APB to the peripherals. And then finally, we have the ATB, which is the advanced trace bus. And this is typically used for debugging software. So for example, if you use the Vitis Unified Development Environment, uh, and you have a Xilinx AMD FPGA plugged into your PC, that will communicate over JTAG using the advanced trace bus to debug your software while it's running. But to what we're talking about today, AXI, which is the Advanced Extensible Interface, what this is a specification that communicates to developers how to signal between two different peripherals or a master and a slave module in a common way, so that if everyone follows this specification properly, you can have coherent communication between those devices. Under the AXI specification, there are three subfamilies. The first one is the AXI memory mapped, and we're going to go into what that means and what that looks like. We also have AXI stream and AXI lite. And the purpose of today's call, webinar, is to go through each of these flavors and discuss what they're used for and what the differences are and how to include them in your designs. I do have a question here asking about an AXI interface to an IP Ethernet PHY. It was not originally doable, but it has it improved now. That's a great question. For AXI-based Ethernet peripherals, I will show during the demonstration the IP catalog to show some of those IPs that are available, and many of those peripherals have a AXI interface to communicate with them. Typically, that might be AXI stream or AXI memory mapped or AXI lite, and I will be sure to cover that. So there's a few basic concepts here that we'd like to go over. The first one is, what is the definition of AXI? How is AXI implemented? What the relationship is between master and slave interfaces? And finally, AXI shims, interconnects, and other IPs, helper IPs to utilize AXI in your designs. So the biggest point about AXI, and this is something that many designers tend to get hung up on, is that AXI is not a bus protocol. AXI is an interface description. And in that interface description, it specifically only allows for point-to-point connections. That is, a single master can talk to a single slave device. So it is not possible within the definition of AXI to have two master devices talking to a single slave device. It is also not possible to have multiple modules on a common bus and have a master talk to multiple slaves in that manner. So we're going to get to this in a little bit for how do you get around that? How does that work? Because obviously, if you've worked with AXI before, you've probably seen where you have one master talking to multiple slaves or multiple masters talking to multiple slaves. And so it is possible to do this, and I'm going to communicate the mechanism by which you're able to do that. It's also important to note that AXI is not a physical standard. It doesn't specify voltage levels. It doesn't specify the clock speed that it runs at. It purely specifies the interface and how data gets communicated from the master to the slave. So by definition for AXI, it allows for unaligned data transfers. This is that I can have a processor talking to a peripheral, and the order that I send out my read and write requests, they do not have to be in the same order. I also have the ability to burst transactions. This is typically used when you're doing a DMA, a dynamic memory access. You can also have multiple outstanding reads, and what that means is that the interface will not get held up if it doesn't get a response from a particular request, and I will talk about which mechanisms can cause that to occur and where you might run into that in your design. I do have a question here on, will you speak about custom IP AXI interface? And yes, I will be getting to that. That is at the very end of our conversation today. So I will be covering that. So the AXI specification and its subfamilies, you have the AXI memory map, which is all encompassing of the entirety of the AXI specification. And then you have AXI lite, which is a smaller subset of signaling and features within the AXI memory map specification. And then finally, an even further smaller subset is the AXI streaming protocol. So they're all very similar in how they work together, though as you go from memory map to streaming, there's some reduction in functionality in order to have higher speed interfaces or more efficient data transfers. So the master-slave relationship within AXI is that master devices are what are known as initiators. So only initiators can cause a transaction to be created. The way that an initiator will implement a transaction is there is a signal known as T-valid, and this valid signal, when that is asserted high, that will tell the slave device that there is something valid that the master device wants the slave device to either accept or respond to. And the way that the slave device will respond to that request is by asserting or setting high the ready signal. So the master device asserts a valid, the slave device asserts a ready, and on the same clock cycle where a valid and a ready are high, that is when a transaction is considered to occur. So initiators can be a processor, it can be a DMA controller, and it can also be custom IP that you've created. It is also possible for a single module to have multiple masters or multiple slave interfaces all within a single module. And we'll show some examples of what that might look like on the next slide. We're primarily talking today about AXI 4. There are previous versions of AXI, such as AXI 3, and not all of those examples or those versions are directly compatible with each other. And the way that we make them compatible between each other is by using logical shims. And these shims will convert the signaling in AXI 3 over to the signaling in AXI 4. And so there are IPs that exist that can be used to handle that conversion. The other thing I want to show here is for the example of if I have multiple slaves or multiple masters, remember AXI is point to point. So I can only have one master communicate to a single slave device. So if you can imagine on the input over here, I'd have a master interface talking to the slave, and then these three master interfaces talking to external slave devices. So many of you may be familiar with something known as an AXI interconnect or an AXI smart connect, or you could have AXI routers and switches. And the idea here is that this module, the insides of this module, do not necessarily have to speak AXI. It's just that the boundary, the interface, is what's speaking AXI. And that allows you to connect a single slave to a single master or multiple masters. There are many different ways that you may want to use AXI within your design. A common way within the AMD ecosystem is through using a SoC device or an MPSoC device. This is where you have within a single FPGA chip, you have a processing system that has a few ARM cores, and you also have programmable logic or FPGA logic in the same chip. And one of the primary ways for the processor to communicate with your peripherals in the FPGA is to communicate over AXI. So that's that first example at the top. The second example at the bottom is, say you just have a standalone FPGA with no processor. You're free to create your own AXI masters and slaves. For example, the memory interface generator within Vivado is a common way to interface with DDR memory interfaces on a PCB, on a printed circuit board. And that typically utilizes an AXI memory mapped interface to facilitate that communication. On the right here, you can see there are many other types of IPs that all have AXI interfaces available, and many of these already exist in the Vivado IP catalog. So now that we've gone over some definitions, where you tend to see AXI be used, let's actually talk about what is the interface? How is the interface described? So when covering AXI full, we have to first look at AXI as having 5 independent channels. We have a write address channel, a write data, and then to confirm from the slave device that the write occurred, there would be a write response. And then to read data, we have the read address. And the way that the slave device communicates that it acknowledged the read is that it hands you back the data that you were expecting. So that gives us our 5 channels. In the AXI memory mapped format, here we can do bursting transactions. So I can provide a single address and send multiple words of data based on how I configure my burst channel or my burst field in my transaction. So here in this just simple example, we have a single address and we're providing 3 data words. And when the 3 data words complete, the slave device provides a response that it got those 3 data words. Likewise, I can do a request for a burst of data from the slave device, and then I can read back those 3 data words as well. Based on the AXI specification, each of those times that a piece of data or data word is sent over to the master or the slave, that is what's known as a data beat. So you can have up to 256 data beats in a single burst. So that is how you'll typically see AXI being communicated. Another facet of AXI is the size or the data width of the data field. The data field can be anywhere from 32 bits up to 256 bits in an AMD FPGA. The specification does allow for data widths of up to 1024 bits. Though keep in mind that as you increase those bits, it would be required to maintain coherency across the vector of data bits. And so you can imagine that for 1,000 bits, it can be very difficult to meet timing at high speeds if I have to keep track of 1,000 bits altogether. And so that's why AMD typically will set the maximum memory map data width to being 256 bits. AXI memory mapped also has the ability to do out of order transactions. And so an example here is that I have 3 read requests, but those read requests have different amounts of latency for response. And so what we can see here is that even though I sent read request 1 first and read request 3 last, read data 3 can come back sooner than data 1 or data 2. And the way that this is facilitated is through the ID field. So if I send a read request with a specific ID number, the response would have to come back with that same ID number so that I would know that that transaction was completed. There was a comment in the chat about the data bit width being dependent greatly by the type of peripheral, and you're absolutely correct. Depending on the interface, that may specify the bit width that is required. For example, depending on your clock speed for 1 gig Ethernet or 10 gig Ethernet, you might have a 64-bit wide interface, or you could have a 128-bit wide, or depending on the line rate, you could have even up to 256 bits wide. There is a fairly straightforward way to calculate based on the data rate, your clock rate, and how wide that data would need to be so that you can meet your bit rate or your line rate specification. Now, AXI Lite is just like AXI Memory Map. It still has the same 5 channels. It has the write address, the write data, the write response, the read address, and the read data. However, you cannot burst. You cannot have bursting transactions. You can only provide a single data beat per clock cycle. Typically, AXI lite interfaces are used for command and control or status. That is, you have a processor that you want to tell your peripheral, set this register value to 10. That would be a single transaction, single AXI communication. Whereas the AXI full is typically used for moving large amounts of data from one place to another, with the purpose of not having the processor need to do every single individual AXI transaction for each consecutive address space. So that's the benefit of AXI full, is that you can, program a DMA engine to do data bursts, and you do not have to monitor uh, every single beat. There is another question here. Is there a number of bytes per cycle specified within AXI? And I guess if I could clarify that, the per clock cycle, you can transfer a single word. So if we were to go back to the slide here, if I can specify, I can make my AXI interface run at 300 megahertz if I'd like to. I could, as long as it meets timing, I can set it to whatever frequency. The frequency is not part of the specification. It's just, can my device meet timing at that speed? But for every clock cycle, depending on what the size of the data field is, that will be how many bytes I send per cycle. So if I'm running at 100 megahertz and I'm doing a 32-bit wide, then that means every 10 nanoseconds I'm sending four bytes. Whereas if I specify it as a 256 bit wide, then that would be 32 bytes. I am seeing here that there are a few folks that are having some trouble with my speaking and the slides. Unfortunately, I do not have any control over that. That's facilitated through Zoom. So if you are running into any of those problems, the easiest thing to do would be to close the session and come back, and that will hopefully resynchronize it for you. So like I said, AXI streaming AXI Lite will allow you to do a single datum. I do just want to cover a few other questions here. So the data width can be up to 1024 bits, and that is correct. You can have an interface that is 1024 bits, and for that 1024-bit interface, you just have to be able to meet timing at it, which can be difficult for such a large number of bits. And so generally it's recommended to stay at 256 bits or less. There's another question here on if I could talk about the difference between AXI Lite and full. So AXI Lite is to do command and control, have a processor set particular register values, like turn on LED 3. That could be programmed to a register. That's typically an AXI Lite application. An AXI full application is for moving large amounts of data. So I might have data that I'm taking from an SD card and moving it to DDR. I can facilitate that with AXI memory map. There is a question here, is bursting the only difference between AXI Lite and AXI full? And that is one aspect of the burst. It is also the out of order transactions. So AXI Lite does not support out of order transactions. Also, another question here is, can I explain the beats in a burst? So there is a field within AXI full that you can specify how many total bytes you're going to transfer. That is the length field. And from that length field, that will determine, I have the length, and then I also have the width of the size. So I can take the length divided by the size, and that'll tell me how many beats I'm supposed to have in a burst. So if I'm trying to do 16 bytes and I have 32-bit width, then that means I have to do 4 beats to transfer all 16 bytes in that single AXI memory map transaction. Does that clarify that for you? So like I said, for the AXI Lite specification, I'm now on slide 18. The main difference here is the out of order transactions. You cannot do that in AXI Lite. You can only do a single data transfer, and there is no burst control. So typically you'll find this when you're configuring a peripheral. So just as a comparison here between the signals that you'll typically find in AXI Full and AXI Lite. And now keep in mind, not all of these signals are always required as per the specification, but they are all included in the specification if you had a use for them. But you can see that the AXI Lite is a very reduced set of fields compared to the AXI memory map. And so typically folks may choose to use AXI Lite because it could be easier to stand up in a design. It can also, take up less space, be more efficient, be quicker to get working. The one main piece that I do want to take note of is that if you look for each of the 5 channels, the AR valid and the AR ready is the one handshaking mechanism specified by AXI that when those 2 signals are both high, the clock cycle where they're both high, that is when the transaction occurs. So you have a valid and a ready for the read address, for the write address, for the read data. You have it for the write data as well as the write response. One other further clarification on AXI Lite is where AXI memory map can allow for data widths of up to 1024 bits as part of the specification. AXI Lite only allows for 32 bits or 64 bits. And most commonly, like there could be reasons why you'd want to use a 64-bit wide AXI Lite interface, though commonly I find that it is 32 bits. Most peripherals have 32-bit data widths for configuration, especially if you have 32-bit wide registers that you are talking to. And then finally, we have AXI Stream. So AXI Stream as an even more simplified version of the AXI protocol. Here, there is only a single channel, just the write data channel. There is a T-valid and a T-ready. There is also a T-last field, which is used to break up transactions. And you have your data field. Now, there is just a slight error on the graphic. The T data field has to be multiples of 8 bits. So at a minimum 8 bits, and you can go from 8 bits to 256 bits wide in an AMD device. There are cases where you may want to go larger, but generally it could become more difficult to meet timing at those data widths. All right, so AXI Stream only has the write data on the master to slave interface. There is no mechanism within any of the AXI protocols for a slave device to talk back to the master device unless it was initiated by the master. So if you do have a slave peripheral that needs to communicate back to a processor, in those cases, you would implement a master interface to then talk to the slave interface of that processor. And that is typically how that would work in your embedded design. Do want to spend a little bit of time here discussing AXI-related cores that exist within the Vivado IP catalog. So I'm going to go through now the data FIFO, the traffic generator, performance monitor, different types of data movement, and the protocol checkers. So the first one here is the AXI data FIFO, and this allows you to buffer or smooth out the flow of an AXI transaction from one peripheral to another. One place where you might use this is that if you have AXI transactions occurring across multiple clock domains. You can have a different clock domain on the read side from the write side, so you can facilitate that clock domain crossing. Typically, this is just used as a way to make sure that a slave module does not get too many transactions that it's unable to handle it. The next one here is an AXI data mover. And so this is a lightweight DMA. It's meant specifically for continuous memory blocks. And it can support some basic AXI bursting transactions from memory mapped to memory mapped transactions. Now this next core, the AXI DMA, and there's also an AXI C DMA, these have the AXI data mover inside of the core. So there's extra logic in these cores to instantiate the AXI data mover. And so not only does this support scatter gather transfers, which are typically advantageous when talking to DDR. So DDR, it doesn't really like to talk to continuous memory regions. So it is better to do a scatter gather and mix reads and writes. So an AXI DMA with scatter gather will get more performance from DDR memory. It also allows you to convert from AXI streaming to memory mapped to talk to memory map peripherals. So an AXI DMA is one core to facilitate that. Now, when it comes to verification and validating your design, there are protocol checkers in the IP catalog that you can use. So there's protocol checkers for the AXI full protocol as well as the AXI streaming protocol. And you can hook these checkers up to your modules that you've created that have AXI interfaces. And when AXI transactions pass through them, it will put console messages in the simulator that tells you which part of the AXI specification might have been violated. So it's a very handy way to see if your design is what would be considered AXI compliant. AXI Performance Monitor. This is where if you're unsure of how often, say, a processor is talking to your module, this can allow you to get statistics on how often transactions pass through the module. It's a fancy AXI counter, basically. So this will let you know if your design is working efficiently. AXI Traffic Generator, we actually use this core often here at BLT. The primary way that we use this core is to generate stimulus data for testing designs on the bench. So maybe we haven't created our entire data path yet, but we want to make sure that the DDR on a board is working correctly. We can use the traffic generator as a way to quickly send read and write transactions to that memory interface. There is a question here on whether or not the protocol checkers are synthesizable. I would have to double check that. I don't believe they are. I believe they are meant just for simulation purposes. And my understanding is that if you try to synthesize with them, it makes them as wires. So it synthesizes out and it just becomes wires from the master to the slave. So it to the compiled bit stream, it would look like it's not there. And then finally, there are other related cores, and I will show you in the IP catalog where to find them and what they look like and the cores that are available. So finally, the last piece here is, how do you incorporate AXI into your design? And one easy way to do that is through using the IP integrator tool. Here you can place AXI-based IPs into a block diagram, and you can click and draw connections from one AXI IP to another. And as long as the master side is talking to a slave side, you'll get a little check mark that allows you to connect the two. Also, if you're creating your own peripherals, you can actually, if you use the correct naming convention, Vivado will automatically determine that, oh, this is an AXI interface. It can determine if it's a slave, a master, it can determine if it's a memory mapped, a lite, or a streaming interface, and it will automatically convert it to a stream, to an interface icon in the block diagram to connect to other pieces of your design. If for some reason your naming convention isn't working, you can also add attributes and Verilog parameters to force the tool to recognize it as an interface. So finally, I just want to share, before we get into the demonstration, of where you can find some additional resources on AXI. The first one here is User Guide 1037. So here, this talks about how AXI works within the AMD Xilinx ecosystem. There was a question earlier on how can you learn more about the AXI full signals like AW cache and AW protect. Those would actually be under the ARM AMBA specification. And this is something that I highly recommend that engineers who are using AXI should download a copy of this specification to their desktop. It's a very good resource and it provides information. So for example, you can put AW cache, you could search for that in the document and that will tell you exactly how those fields are used and what you should set those values to. There is one other question here on, is there a spec for interconnects? Is the ID field simply a counter? Do interconnects modify the ID field, especially in something like a cross-point interconnect with multiple masters and slaves? So that is a very complex question to answer. It really depends on an application by application basis. For example, I've worked on designs where certain IDs had a meaning. So we used certain IDs to say, this is the device that was sending that request. So that's one way that you can see that. So really, it just depends. Some places it might be a counter, like it might say, okay, start at this number and then count from this number to this range, and those are all the IDs. So it really depends on the application, and you'd have to look at the processor specification for how it chooses to use IDs. All right, so that concludes my lecture. So I do want to now switch over to a virtual environment so that I can show some examples here. So here I have a virtual environment that I've preloaded two AXI examples. I have first here an AXI traffic generation. And the way that I created this was actually very simple. If you take an AXI traffic generator IP, like this one here, if you right click on the IP, you can do open IP example design. And so this gives you an example design that you can run in simulation directly. So it's a very convenient way to learn a little bit more about AXI and how AXI works within Vivado. Before I run this demonstration, I do also want to show, if I go to the IP catalog here, and if I type in AXI, there are 275 matches for different AXI type IPs, some slow ones, some higher speed like Ethernet and USB. There are many different types of AXI IPs available. So what I'd like to show here is if I take a look at this test bench file, and this test bench file instantiates the traffic generator, and it's configured in a loopback mode. So there are going to be transactions that will come out on the master interface, talking to the slave interface of the traffic generator, and we will be able to take a look at those signals to see what AXI transactions look like. So I'm going to select Run Simulation. There is a question here on, in simulation, how do you tell light versus full? And honestly, for me, the way that I tell the most simplest way is I look to see if there's an ID field. If there's not an ID signal, then typically it wouldn't, or bursting signals, then it would be a light versus a full. If we go back now and add some signals to look at on the interface here. So here I have my slave interface, and then there's also the master interface. It is operating in a loopback mode, so I'm going to just select the master interfaces to make it a little bit easier to see. All right, so and then I'm going to run it to completion. And now let's take a look at the signals. To run it a little bit longer. Do apologize for the zooming. I was trying to come up with the simplest way that we can show this example and that everyone could see it well. Let me minimize that. So if I take a look here, I have a read request. So I can go, and this is completely random. It's using the traffic generator. So this time when I ran it, it was running with a read example here. So if I take a look at the address field, that's a 0. The AR valid should go high at some point. So earlier on, there was a read valid on the address, and that read address was set to this value here at that clock cycle, and it was accepted by the slave. The ready is just constantly high. So if the clock cycle where the ready and the valid is high, that's when that transfer occurred. So that told the slave device to expect a read request. And I can also see here that it's expecting a burst because burst is set to a 1. And I can also see that it's expecting a burst size of 2 based on what's specified in this field. So now if we look at the read response side, I can see that that 2, now keep in mind the size does not actually correspond to how many words you will have. It's specified in the AMBA specification for what it means. So in this case, it will be 4 words. So what we can see here is if we look at our valid is high for 4 clock cycles, ready remains high, and I have a 0, a 1, a 2, and a 3 as my 4 words. So that is an example of a memory map transaction. There are a few other fields here. I encourage you to go look at the specification to understand what's happening in the other fields. There is a question here asking on if I can show a block diagram for this demo. This demo does not have a block diagram. It is purely the connection of the AXI traffic generator core. So what I can show included in this example is there's a AXI lite driver that's sending transactions to the traffic generator, and there's a block RAM on the output. I don't have a block diagram of this, but in the middle we have our traffic generator, and this has a slave AXI interface and a master AXI interface, and these ports are connected in a loopback. Now, when I switch over to my other example, I do have a block diagram for that, so I will show you that. So now switching over to the AXI streaming example, here I have a block diagram. And so we can see in this example that we are using the AXI verification IP. And the AXI verification IP allows you to emulate a master device, a pass-through device, or a slave device. So this block diagram here can be all three. And in my test bench, I have it specified as a pass-through. And if you take the AXI verification IP, and if you right click on it and say open IP example design, that is how I got to this starting point. So it's a very straightforward way to get a test bench to test that your AXI is working correctly. So once again, if I run the simulation, here what I'll show is what an AXI streaming event looks like. So let me just clear out some things here. I'm going to add one of the AXI interfaces. So there is a question here, if the AXI VIP was one of the cores, you said it would synthesize out, and correct, the AXI VIP would synthesize to wires. The question before was on the protocol checker, and I believe the protocol checker would synthesize to wires as well. So here, if I look at my slave AXI interface, let's make this a little bit smaller, and let's run it. So now if I go back here, I can see I have a lot more transactions occurring. Let's zoom in to a particular transaction. Keep in mind that an AXI stream does not have bursting capability. It's just if ready and valid are high, data transfer occurs. There is no mechanism for counting the number of bytes that were transferred as part of the specification. And here we can see, for example, that when valid was high, the value E was sent over. We can also see that the value F was specified as the keep value. So the keep is in an AXI stream, you might not want every byte to be considered valid. So in this case, F is considered valid because it's for four bytes, but you can have a wider interface where maybe you don't have everything valid. There could be examples somewhere in here of different configuration. I don't have control over the data that's presented here. It's all random. It was based on the verification IP that is specifying this. Now, it is possible to configure the verification IP for your own example data. That would be a topic for another day, but that is possible as well. And we can see here, for example, on this transaction, when ready and valid were high, then there should be a data field. Here's the data field and a few other sideband fields as well, such as T-last. You can have IDs and destinations as well as additional sideband information. Sometimes the T-user field is used as a mechanism. If I have an ADC connected and I'm collecting samples, maybe I put my over range or over voltage information in the T-user field. There's a lot of ways you may want to use it. So that completes my demo. That was really the hope today, was really just to share what is AXI, how is AXI used, where you might run into AXI. I see that there are a few other questions coming in here, so I will address them. Before I do, I'd like Sharon to step in here with some additional information.
Hi guys. Since I'm in marketing, that's my job, is to come here and tell you about some of the other things that we're working on. So if you liked this webinar, Ellie is also doing a webinar in 2 weeks, which is on RF stocks for space applications. So I will drop the link into the chat panel for you if you're interested in attending that event. And if you're interested in learning a lot more about AXI, we have 2 classes coming up that go more into depth on AXI. So one of them is our Vivado Bootcamp 2, and that's coming up in a couple of weeks, I think in 2 weeks. And then we have our embedded hardware bootcamp in January. So I'll put those links into the chat panel as well. And if you're interested in our complete webinar series and workshops, which are 4 hours long, I will put the link to that page so you can see everything that's going on. We've got a whole bunch of things coming up, and the 2024 schedule will be out shortly. I have not posted that yet, but it will be live soon, so you can register for all of the 2024 events that we'll be doing. So I'll go ahead and put those links in. And if you want to reach out to Ellie, I will also put in an email address if you have questions that you want to take offline. So Ellie, let's go ahead and get to some questions.
Sure, I can go through them. But,
Okay.
so the first one here is there a way to convert APB AHB masters to AXI and Vivado? And there should be a way that you can do that. If you go to the IP catalog, there is an AXI APB bridge, for example. So that's one IP that's available to do that conversion. There is also AHB variants as well. So all exists in the repository for you. Another question here is, what's the difference between the traffic generator IP and the AXI master VIP? So the AXI master verification IP is only meant for verification. When you go to run synthesis, it'll be converted to wires. It'll effectively not exist in your design. Whereas the traffic generator will create logic in your bit stream so that you can continue to create traffic on a real piece of silicon. So that's the main difference between the traffic generator IP and the AXI master VIP. Another question here on, is there a verification IP for the AXI lite slave interface? And there is. You can, let's see here, if I open up the block diagram, I can load in a AXI verification IP. And then from this verification IP, I can specify which protocol it is. I can also specify which signals are available as well. So you can use this for AXI lite or AXI memory mapped. So that's one of your options there. Another question here. Are there differences of the AMD implementation and AMBA specification? I know about that based on AMBA, T-ready should not be low without transaction after it was high. In AMD, it is allowed. I may have to go back and re-verify that. For example, and I know that the protocol checker does check for this, is if you assert T-valid, T-valid needs to remain high. I don't believe there's any guidance on whether or not T-ready needs to remain high. I think you are correct that AMD in some of the IPs will not assert T-ready until it gets a valid. So some IPs will just always keep ready high, whereas other IPs will say, let me wait to see a valid request, and then once valid comes in, then I assert ready. So that it really depends IP to IP. But that's one situation that you might run into. There's a question here. I'd like to get started with AXI, but don't have any project ideas. Do you have any suggestions? One of the easiest ways to get started with AXI is to use a block called the AXI GPIO. So the AXI GPIO block, you can connect to signals on your board. So for example, I can take the AXI GPIO and I can connect it to signals on my board. And then that way you can use simple AXI writes to turn an LED on or off, for example. And so that's usually a good way to get started to see how AXI works. Let's see here. What are things that one should consider when porting an AXI design from an SoC like Zynq to the MP SoC device? The biggest thing to keep in mind for that is the Zynq 7000 used AXI 3 interfaces in the processing system, whereas the MP SoC is AXI 4. So if you happen to have a AXI 3 based peripheral, you may need to either implement a shim or take a shim from the IP catalog to be able to convert from the AXI 3 to the AXI 4. That's really the biggest difference that I could think of. Also on the MP SoC, there is support for wider interfaces, so they are backwards compatible. to the slightly less smaller data widths that you'd have in the Zinc 7000. And then another question that was asked is that within Vivado, on the if I'm customizing an MP sock, that there's something called an ACE port. What is the ACE port? What is it used for? So the ACE port is the AXI coherency extension, and this is typically used to maintain cache coherency between multiple processors. So it's similar to AXI. There are a few additional fields for it. And typically you would use an ACE port if you had a microblaze in your programmable logic, which is a soft core processor, and you want to maintain cache coherency with the system and say an MP sock, you would facilitate that through the ACE port. And finally, we have what's the easiest way to create your own IP in AXI. And the easiest way to do that is within Vivado, you can run the create custom IP wizard. And one of those options is to create an AXI IP. And so that will give you a template for creating your own AXI IPs. So with that, I don't believe there are any more questions. I appreciate you all taking the time to join us for our webinar today. And like Sharon said, I'll be hosting another webinar in 2 weeks on the RF SOC. So I look forward to seeing you all there. And if there are any questions, Sharon posted in the chat an email that you can use to reach me.
All right, we appreciate everyone joining us. Ellie, thank you so much for sharing your expertise with us today.